So in this video, we are going to talk about the definite integral, and basically what is the definite integral. And it's this expression you see right here is the notation for the definite integral. And the fastest answer I can give you is that it's net area. So that is something you always want to keep in mind. So you have some function f, and it is the area bounded by f and the x-axis between x equal a and x equal b. So it is net area. So here's an example of what I mean by that. So here I have a function f, and let's suppose that the area that you see in here, so this region in here, let's suppose that that area, an area of 2. And let's suppose that this region here, let's suppose the area of this region is 4. And this little region over here, let's suppose the area of this region is 1. Now, if I wanted to calculate the definite integral from x equal 3, from x equals 0 to x equal 3, so that's from here to here, and of my function f, as I said, this is net area. So what I would do is I would add the area here, which is 2, to the area here, which is going to contribute -4 since it's below the x-axis. And then I would add finally add the area here, which is just 1. So my definite integral would be equal to -1, and that would be my final answer. So that's what I mean by net area. And by net, I just mean that, regions that lie below the x-axis will have a negative contribution. So this is a contribution of +2, -4, and +1 in here. So let's do another example using this idea of net area. So let's suppose I want to calculate the definite integral of x dx from x equal 0 to x equal 5. So this is my function here. So in this case, using the idea that this is net area, I would ask myself, well, what does this region look like? So let's just graph this really quickly. So here's my x-axis, my y-axis. Okay, and here is the line. So my function here is f of x is equal to x. That's just a line through the origin with slope 1. So the region that we're interested in is actually the region from 0 to 5 that is between our graph of f of x and the x-axis. So I want to know the area of this region, and it's going to be that basically it's the area of this triangle. So in order to calculate the definite integral, I would just say that, oh, this is just 1/2 times base times height. So that's 1/2 times 5 times 5, which is 25 divided by 2, which is 12.5. And I would be done. That would be my definite integral. And notice that that triangle was above the x-axis, so that is going to be a positive area. Let's calculate this definite integral. Okay, so again, remember, I'm just going to use the fact that it's a net area, and that's what this means. And so luckily, so I can look at what is this function, what does the graph look like above the interval -3, 3. So I'm just going to graph it really quickly, just a rough sketch. And some of you might recognize this as the top half of a circle with radius 3. So my graph is going to look something like this. And it's the top half of a circle, so this is f of x equal to √9 minus x squared. So I asked, so this expression here, it represents the area, okay, between my curve, the top half of the circle and the x-axis. There's no part that lies below the x-axis. So what I'm asking is, what is this, what is the area there? And so again, we see, okay, that's just a half circle, so we're going to use 1/2 of pi r squared, because this is the area enclosed in a circle. So that is going to be 1/2. The radius is 3. So 1/2 times pi times 3 squared. So that's 9 pi over 2. And that is the answer. So you might recall from the previous section that when we wanted to estimate or calculate the area under a curve F, and it did not have a nice shape like a triangle or a circle or a rectangle, what we did was we used the approximating rectangles and in order to estimate the area, and we added up these areas, the areas of the rectangles, and then we took the limit as the number of rectangles n went to infinity, and that gave us an expression for the actual area. So this is helpful in the general case when it's not a circle, triangle, or rectangle shaped area. So just to, so how does that connect to the definite integral? Well, the definite integral is the same exact thing. So in other words, the definite integral is equal to the area, or I should say the net area. Which in the last section, we developed this formula. It's the limit is the number of rectangles, n goes to infinity, of the sum of the approximating rectangles, right? The sum of the areas of the approximating rectangle. This is exactly what the definite integral is equal to in the general case. This is exactly how we calculate. Okay. And remember, just to give you a little more detail, remember that delta x is just b minus a over n, and xi is a plus I delta x. Okay, so we can calculate those exactly. So let's do an example just to reinforce this idea that the definite integral is actually exactly what we just did with the limits of the Riemann sums. So let's do this example. So I'm going to express the definite integral below as a limit of Riemann sums. Okay. So the first thing I'm going to look at is what are called my bounds of integration. So this tells me that x is between 2 and 5. So 2, 5 is the interval that I am interested in. And this tells me that my function is f of x equal ln x over 3x squared minus 5. So once again, I'm going to go over and I'm going to calculate delta x, which is just b minus a over n. And in this case, that is 5 minus 2 over n, or 3 over n. xi is given by a plus I delta x. So a was equal to 2, and that is 2 plus I times 3 over n. So this is just 2 plus 3i over n. Is equal to, it's just remember the net area, which is the limit as n approaches infinity. So here's my formula. Okay, and so this is equal to the limit as n approaches infinity of, let's do f of xi would be ln of xi over 3xi squared minus 5 times delta x. And since I have figured these out, I'm just going to add them, make this more precise. So this would be the natural log of 2 plus 3i over n divided by 3 times squared minus 5 times delta x, which was 3 over n. So this, you see, is the expressing the definite integral as a limit of Riemann sums. Okay, so let's work the other way. If I were to give you this limit, would you be able to tell me what the definite integral was? So let's just do a couple examples like that. Again, just to kind of get you comfortable with the notation. So we are going to express the limit, so it's a limit of Riemann sums, as a definite integral. So we want to put it in this form. Okay, that means we're going to have to figure out what is the function f of x. That's really the key, because the bounds of integration are usually just given. You're told what interval you're working with. So let's take a look at this. So remember that this expression you see here is, I'm going to write the definition below it so you can see them next to each other. Okay, and so you can see that this is, I've got my delta x here, and this expression we've got up here. So this part right here, this is f of xi. Okay, so this tells me f of xi is xi to the fourth times the root of 5xi minus 3. So that just implies that f of x is just the function. It takes my input, raises it to the fourth power, and then it multiplies by 5 times my input minus 3. So that is my function. And that's really the key of what I need to know. I'm given that the interval I'm interested in is 0, 5. So my definite integral is going to be from 0 to 5. We would like to know the area, or the net area, between this curve and the x-axis. And then the delta x you see here is just like the dx. Okay, it's a little increment of the x-axis. So this would be my answer. Okay, and again, you can see that the bounds of integration are right here. Okay, that's the interval. We're interested in looking at the area. We just had to figure out what f of x was. Okay, and here's another example. We're just trying to express this as a definite integral. So once again, we see the delta x here, and we see the limit in the sum here. So this is my function. This is f of xi, okay, and this is my interval. So in this case, the definite integral would be from 10 to 12. And it looks like my function is 3x times cosine of 5x. And this is my dx. So this would be my final answer in that case.